All right, section 5-7 here is on the definite integral properties. The objective of this section, recall, is to evaluate definite integrals using the fundamental theorem of calculus and using the definite integral properties that we learned in this section. The second half of this section here, I just want to go over the variable substitution technique that you saw with indefinite integrals and how we can use that to help us evaluate definite integrals. All right. So here's the variable substitution with definite integrals. Sometimes we call it a u substitution because we usually use the variable u as our variable of choice. So that's the first step, is to let u equal part of the integrand. And usually if it's a composition, at least for all the functions we've seen so far, you're going to want to pick the inside function as being your choice for u. Now once you pick u, you then have to calculate or derive du. Take the derivative, or find the, I should say, the differential of u by taking the derivative of the equation that you set equal to u. And then multiplying that, of course, by dx gives you du in terms of x and dx. And basically when you get that equation there, you want to keep all the u's on one side, so the du will be on one side, and you want to keep all the x's and dx's on the other side. It's okay if you want to move constants from one side to the other, but keep the x's and dx's together on one side. So that gives you u, and that gives you du. Now since it's a definite integral, you have upper and lower bounds, and those upper and lower bounds are defined in terms of x. You're saying you're finding the definite integral from x equals a to x equals b, so you've got some sort of an interval there. And now we're changing this over to a new variable u, so I have to get my upper and lower bound in terms of u. So use the equation for u to find your new upper and lower bounds. Just simply take your x value, plug it in to that equation for u, and it'll tell you the corresponding u value. Do the same for the for both of those, the upper and lower bound, and you got yourself a new upper and lower bound in terms of u. And then finally, substitute u and du back into the problem and solve. Just like you have already solved problems that involved x. In fact, you've seen some that have involved other variables like t and so forth. It's the same type of problem there now, it's just in terms of a new variable. The nice thing about this is that you don't have to go back and substitute in for u at the end, because you've completely changed it over to a new variable, and you're just solving that equation in terms of u, and so, and including the upper and lower bounds. So therefore, the number that you get out at the end is the number that you're looking for. In essence, this is what we end up with here. You have to think of your problem in this way. That you've actually got a composition, again, is usually what we're working with here, where you've got f of gx, f of g of x, which is your composition, and then it's multiplied by the differential of the inside function. That's the g prime of x times dx. So our choice here for u is to make u the inside function. So you'll see over here that we're making u equal to g of x. We then have to calculate what du is equal to, and notice that du turns out to be the g prime of x times dx. Sometimes there's a little bit more that we have to do with that. It might have a constant or something like that that we have to deal with, but in general, this is kind of what it looks like. And then you rewrite this in terms of function u now. So the last step that we talked about was changing your upper and lower bound. You'll notice that I've changed my lower bound. It was going from a to b. Now it's going from g of a to g of b. And the way that I got that is because I took a and b and plugged them into this equation over here for u. And that tells me how to find the upper and lower bound in terms of u. And so now you're integrating f of, instead of g of x, it's f of u, because u equals g of x. And instead of g prime of x dx, it's now du. So that's the problem. It simplifies down to just f of u du, and then you integrate that. Whole idea here is that you've simplified the problem. Obviously, if it has not become simpler by doing this, then go back to the original. So that's the easier one to work with then. All right, let's take a look at an example of this and try using this technique. So here you can see we have the definite integral from 1 to 2 of 3x minus 2 to the 4th times dx. I've got a composition here. So this looks like ideal to make the u substitution here. I'm going to make u equal to the inside function, the 3x minus 2. And When I pick u, I have to then calculate or derive du, the differential of u. Derivative of 3x minus 2 is 3 times my differential of x. And you can see that I have a dx over here, but I don't have a 3 with it, so I'm going to move the 3 to the other side. This is what I said. It's okay to move a constant over there with the du, but you don't want to move x or dx over there. So now I have a variable substitution with u equals 3x minus 2, and I end up with my differential dx is equal to 1/3 du. So let's make our substitution here then. I'll wait on the upper and lower bound for just a second. Let's first rewrite this as, instead of 3x minus 2 to the fourth, it's going to be u to the fourth times, instead of dx, it's 1/3 du. And your upper and lower bounds, if I take this value of 1 here, and I plug it into my formula over here for with x equal to 1, I'll end up with 3 times 1 minus 2. In fact, I'll go ahead and write that down below here. I end up with u equals 3 times 1 minus 2 when I plug in the lower bound. And so that ends up giving me 3 minus 2 is 1. So my new lower bound is 1 in terms of this new function u. Do the same thing for the upper bound. U equals 3 times 2 minus 2. So that's 6 minus 2 is 4. So my new upper bound is 4. So my lower bound didn't actually change, but my upper bound did. It doesn't always work out that way. Sometimes it turns out that the bounds might be the same. Just depends on your function and the points you're plugging in, obviously. And if you want to, the 1/3 is a constant. It can come out front. That's one of our properties of the integral of a constant times a function. Is the constant times the definite integral of your function. So you can bring that out front. And now again, before you integrate, check to see if you've simplified this problem. I think we've definitely made it easier here. Just a power function, obviously. And it's not a composition. So now just integrate it just like you have been doing using your fundamental theorem. The antiderivative of u to the fourth is 1/5 u to the fifth. And we're evaluating that. Oops, I lost my 1/3 out front. There's a 1/3 times that. And we're evaluating that from 1 to 4. And we don't have to substitute back in terms of u because my upper and lower, or back in terms of x, because of the fact my upper and lower bounds are in terms of u, so I can just plug u directly into this. So I end up with 1/15 times 4 to the fifth minus the 1/15, that's the 1/3 times 1/5, times 1 to the fifth. And 4 to the fifth, what is 4 to the fifth? Let me quick punch that in my calculator there. We get 1,024. So we get 1,024 over 15 minus 1/15. So I guess I'll just leave this as 1,023 over 15. If you want to simplify further from there, you certainly could, but I'll leave it just like that. In fact, sometimes it's nice to just simply put that in your calculator, put the antiderivative in your calculator. If I go to y1 and put in 1/15, and then x to the fifth was our antiderivative. And then on my home screen, I can just tell it to take y1 and evaluate it at the upper bound, minus y1 and evaluate it at the lower bound, and get 68.2. And you can check to make sure that the value we had written down there, the 1023 divided by 15, is the same result, 68.2. I'll go ahead and write that down here, 68.2. You can write it either way, obviously. Okay. There is our variable substitution with a definite integral.